Now we're going to talk about the non-blocking interface. And again, to remind everyone, Ruth said we had a lot of functions in MPI. Non-blocking is like a concept that is orthogonal to the other functionality that we have learned about yesterday in point-to-point. Yeah. So what we'll so for all the functionality that you saw yesterday, the different send modes like a B send, a synchronous send, S send, the standard send, for all of those, we'll have a non-blocking part. And also, we'll learn about blocking collective communication. And we don't have the time to learn about non-blocking communication, but it'll be extending this non-blocking concept to the collective communication as well, right? So what you learn here now with point-to-point communication will be transferable to collective communication later on, right? And also to file I/O once you look into parallel file I/O, which we can't cover in this course in those 2 days. All right, so what we already learned about non-blocking communication yesterday is that a non-blocking procedure returns before the operation that's associated with it is complete locally. Yeah? So that means if it is incomplete, that's why sometimes, we'll come to that, well, sometimes the functions have an I to it for incomplete or immediate. That's sometimes debated what the I stands for. But let's call it incomplete because it suggests that you need something to complete the overall call. So a separate call is needed to complete the operation that's behind it, because when you just say, well, I start something, you want to know when things are done, right? You want to know when you can reuse your buffer. You want to know when the receive buffer is filled so you can work on the data that you wanted to receive. Yeah, so we need something, we separate those two functions, so we need something to connect those two calls. The first one to start something, to start the operation, and the second one to end it. And to connect those two, there's a new handle type that is the so-called request handle. Okay, so in C, it has its own type. Again, MPI underscore request. In Fortran 90, it's a normal integer, and Fortran 2008, it's this type leaning towards the C type in the interface. So what you should not assume, yeah, is that you will see asynchronous progress when using non-blocking communication. What is asynchronous progress? Asynchronous actually means, again, without intervention of the remote side. Yeah, so it could be that the overall time you need for the send function is actually the same or slightly bigger, but let's assume the same if you add the time you need for an ISEND or for the starting the non-blocking send and for completing the non-blocking send. If you add those two things together, then those two things may actually use the same time, and you do not have any computation communication overlap. But what basically every MPI serves, so there's no guarantee for this, but what usually happens is as long as you are in MPI, those MPI functions will try to provide progress as good as possible, right? So you will, for example, see communication progress if you're within for example, a barrier or so. An MPI function that is not associated with point-to-point communication. Yeah, so because then the MPI has control and the MPI can progress any incomplete operations that are still ongoing. So sometimes MPI implementations provide a progress thread. That means they spawn an additional thread that just tries to progress communication. But that is also expensive because that thread has to run on some computational resources. Those might have impact on the other resources that you have in for your application threads, or the processes, meaning it can have an influence on your cache behavior and so on, because the progress thread will also use the CPU. So it's oftentimes not enabled by default, but you can check the documentation of that specific MPI to try to enable that and see how the performance is. Some applications benefit from this, others don't. So you always check whether your application actually benefits from having a progress thread or not. And sometimes you can even have hardware support for specific transfers. The keyword here is, for example, RDMA, remote direct memory access, that, for example, if you have a contiguous buffer, let's say 8 integers, some network cards, you can just say, this is the pointer, this is the size, please do it for me. And then the rest is completely handled by the network interface. So there you might actually benefit from computation communication overlap. Okay. So, but so you can use it for computation communication overlap, but the key idea is that it makes it really easy to avoid those deadlock situations that we saw yesterday when we used either send receive or we used the checkerboard pattern. With non-blocking communication, it makes it really easy to have all processes do the same communication pattern without running into the dangers of being deadlocked. Okay, as I already said, the I stands for immediate or incomplete. But beware, I also said that yesterday, not all of the functions have that. Most of them do, I would say like 90% in MPI, the non-blocking interface has this, but there are some functions that don't have this, but still are implicitly non-blocking. One example would be MPI put, MPI get. Those two belong to the one-sided communication interface, which we don't cover in this course. Okay, so, and it's capital I because the I is usually directly after the underscore, directly after the underscore. And that, as we saw in the nomenclature and how the C interface is written, the letter behind the underscore is capitalized and the rest is lowercase. So now it's MPI I send. And if we look at the argument list, we have the same as the send, but now we have an additional argument, which is this request, and it's an out argument. And that's why it's also, again, at the end. And the I receive now also has the same argument list, but now the status object is replaced by request object. So why is that? The status object tells us about our communication after it is completed. It can't tell us anything about our communication before it is completed, right? Because we don't know the state. We don't know which message it actually matched with, right? So it doesn't make sense to have a status object here, but we connect it to the completing function, and then the completing function will give us the status object. Okay. So, how do we complete these operations? So, and then there are two families, I call them, and within those families, we have 4 different types of waiting for the completion. So the first one is when we block for completion. So that is a blocking call again, and it's called wait. And what we do there with the blocking for the communication, there we return the status object, but then the same thing applies what we said about status objects with an MPI receive. Yeah, if you need to investigate the status object, provide a status object, so MPI can fill it. If you don't, provide MPI status ignore, and then this status object is omitted. So, within the family of blocking completion for non-blocking communication in general, you have a call that's wait. That's called wait. And the whole family has a wait and then some suffix to it. The general, or the easiest one to understand is MPI wait, gets a single request and returns a single status. Yeah, and here the request is the input, or it's an in-out actually, and this is an out argument. So the second one is you have multiple requests and want to wait for any single one. Yeah, so you now place an array of requests in there, and you have to provide the number of entries in that array, and it returns the index in that array back to you and the corresponding status object if you didn't provide status ignore. Yeah. So the next one, to make it more complex again, is MPI wait sum. You also provide an array of requests. So we have that again. And again, we need the in count in terms of how many requests are initially in this array of requests. But now, instead of getting the index of a single entry in that, you get the number of entries out, and you need to provide this array of indices, and it tells you the indices into that array that have completed. And then you also need a status array for all of these completed ones. And because this is now a different type, it's no longer a pointer to a status object, but it is a pointer to an array of status objects. So here you have this slight change in nomenclature here. It's not MPI status ignore, because that's a type def to a specific pointer to a status. Now it's MPI statuses ignore, and that is then from the type of a status of a pointer to a status array. So when you don't have any active requests, and we kind of learn about what that means in a bit, it returns undefined in the out count, meaning, well, all of these are basically already done already. Yeah. So instead of just aborting your application and just says, sorry, you kind of missed that all of the requests that you gave me are actually completed already. So it returns MPI undefined in the count. Okay. Now the last one is MPI wait all. And the semantics there is we don't want to wait for any single one. We don't want to wait for some of it. We want to wait for all of the requests that we want to be investigated or completed. So we provide an array of requests again. We provide the in count or the count in general. Now we don't need an out count, so it gets a little simpler again. We don't need an out count, we don't need an index, we just need the array of status objects for all of the completed requests. And again, this is an array of status objects, so you could put MPI status sys ignore in this field. So those 4 functions, I would usually say, well, this wait sum is in there to allow for optimization on behalf of the MPI implementation. Because there might be several requests that are already completed, and the implementation could hand you all of those directly in one go. In practice, the difference in performance you see on the application level is marginal. So, but this wait sum kind of implies a lot of more code around the wait sum, because now you need to investigate what the out count is, you need to loop over this array of indices and so on. So it makes your application a little bit more complex. And more complex always means harder to maintain. So again, premature optimization is the root of all evil. Yeah. Only try this out if that works for your application if you see a problem with any of the other calls. In practice, personally, await any helps you if you have more than one outstanding, and await all is usually the right choice if you have to wait for all of them anyway. Yeah, and you do not want to do anything in between. Yeah, the wait call is good if you just have one anyway, but if you have more than one outstanding, it could be that you with looping yourself over several requests that you have in your, and do a wait for each of those requests yourself, will mandate an order in which you test for completion, or if you wait for completion. And using a wait any can basically give the implementation the possibility to complete out of your intended order of requests. Okay, so how does this look in a timeline? So if we look back to the sender-receiver example for a blocking send, so this is again an MPI blocking standard send, this is a blocking receive, and in between we're not allowed to use the buffer. So now we have on the sender side, we have a call that's called MPI_ISend, and we have an MPI_IReceive. And the prototypes you already saw. And if you put a wait call directly after this, the semantics is exactly the same as if this would have been the blocking send or this would have been the blocking receive. Yeah, so if you're not doing anything in between, it's the same as the corresponding blocking call. But now what you can do is, now you could put some work in between, and work can be another MPI function as well. Yeah, so, and now this becomes more important, that while you're in between those two calls, you're not allowed to touch any of the buffers, or you're not allowed to modify any of the buffers that you provided to the MPI function. Okay, so how can we use this to our advantage to prevent the deadlock? So, for example, we had the problem that we had the send before the receive, and then depending on which implementation was chosen, if we have a synchronous send, we will wait for each other and we'll create a deadlock. So the problem was that the send will not match with the corresponding receive. The receive was not posted, but we also couldn't post the blocking receive in advance. So what we now can do is we post the receive. So the MPI on the receiver side already knows of, yes, I am expecting something here, right? Then I can post my send, and this send can now match with this posted I receive because the progress is done inside this MPI send, because I said there is progress usually done as long as you are in some form of MPI function. Yeah, so now all of this, I'm waiting for something, is resolved because those two receives are pre-posted. Yeah, and then the wait is basically just cleaning up things for the I receive. Yeah, so you can't forget about this, but the transfer itself is likely happening in here in the sense. Okay, and this is actually, I would say, the most likely implementation inside of an MPI send receive, a blocking MPI send receive that you used yesterday. Okay, so, but you can also just say, well, if I already use one request and one non-blocking function, you can also use two. So you have an I receive and an I send, and then you just say, well, I wait for all of them to complete. Yeah. So, and the reason why you can or why you should consider this as well is, for example, if you have a domain decomposition with a stencil code where you have to communicate north, south, left, right. Yeah, you can just initiate all the stencil communications that you need, depending on the neighborhood that you're in, and then just wait all for everything until things are done. Yeah, potentially you could also just wait for the left neighbors, left for the top, wait for the right. But again, then you're implying a certain order of completion, and if you just continue. When everything is there, everything is completed, then the wait all is the most sensible thing to wait for anyway. Okay, so now that is all the blocking interface. So we had a non-blocking starter, initiator of the operation, and then we had the blocking counterpart that actually waits for completion. But sometimes we don't want the MPI implementation or the MPI library to keep control of my control flow of the application. I just want to know, is this done? If it's not done, I would have something else to do in between, right? And also just kind of poking into, looking into into the request queue, just gives a little bit of potential for progress, because we're again inside an MPI function. So we just want to check or test for completion, and that is the name of this second family. And it does not block for completion. So test in itself is a non-blocking function and doesn't have an I to it. So it's not I test or so. Yeah. So one of the other examples where non-blocking function is doesn't have an I to it. So what it does, it returns a flag that tells you this type of test is either true or false. So it tells you if this would have been a wait, I would have been complete now, yes or no. So, and the same thing is true for status objects there as well. The only thing is that the status object that you provide here only has the corresponding values in there when this flag is true. And this is an integer Boolean, meaning 0 is false and anything else is true. Yeah, so you should basically, your test, whether it is true, should follow the normal test against 0 or non-zero. Okay, again, just like it's this new family, we have testing for a single request. It tells you one request, the flag, is this request yes or no? If this is true, this function behaves as if you would have called wait. That means you don't have to call and wait after this return true. It is all the communication, and this request has basically completed in the background. So same thing here. The test any, you provide an array of requests. The request at index I, when flag is true, that is completed. The rest, it doesn't tell you anything about. And this is also something that I didn't mention in the wait, because there it didn't really make sense. It did make sense for the wait any. So ignore that comment. So here you have an array of requests, and potentially somewhere in the middle something is completed, right? The index doesn't have to be 0, or starting from the front. And you don't want to rearrange your array of requests and always, remove the completed ones from this array of requests. So what MPI allows you to do to provide these completed requests, continuously provide these in this array of requests. You don't have to touch this until all of the requests are basically completed. Again, test any behaves as wait any. All right, so test sum, same semantics, just the non-blocking version of it. And now, but here you don't see a flag, you just still have the out count. Because yes, if there is an out count, at least one was true. If there's out count 0, then of course there was none, right? So you don't need an extra flag here. Status is ignore continues to apply here as well, and you have the test all is the same. So the semantics again, this returns true if all of the requests are completed and the wait all would have returned to you. And then again, as with all test compared to the wait, a test with flag true behaves as if you would have called the corresponding wait function on the specific request that is indicated to be completed. Okay, then again, test and wait will only give you local completion. And I can't stress that enough. So if you have an ISend, it will just tell you, just like with a blocking send, that this operation is completed locally. Yeah. The remote side, that is something that for example, the send modes give you some indication of, but also again, it doesn't really, no function in MPI actually tells you about reception completion other than like a ping pong example that you implement yourself. But usually your application doesn't need that. Usually the local process just needs to know when can I reuse the communication buffer that I have locally. Because I know I can trust MPI, I don't have to resend anything. MPI gives me the guarantee that if it tells me that this is completed locally, I can do whatever I want with that buffer. Okay, so yes, as I mentioned, if something is successfully completed, then the corresponding handle is set to MPI request null. And if you could call any of those with MPI request null, the wait will immediately return, but the status will be empty because it doesn't know anything what it should fill the values with. The test sets flag to true and also returns with an empty status because of the same thing, right? It says yes, a null request is always completed, and I don't have any info to give you. And it is ignored in the presence of other other valid active requests. Okay, and that's basically already the orthogonal concept of non-blocking communication in MPI.